everyone, a warm welcome. In this video, I am going to discuss about two important series in complex analysis, which are Taylor series and Maclaurin series. See, there is one more important series in complex analysis, which is Lorentz series. I am supposed to do another video for Lorentz series. Let me start Taylor series. If fz is analytic at a point A, then fz can be expressed in the form of an infinite series containing positive powers of z minus a, which is in the form fz equal to f of a plus z minus a into f dash a plus z minus a the whole square by 2 factorial f2 dash a plus etc. And this series is known as Taylor series, and it is named after an English mathematician, Brooke Taylor. Taylor series has wide-reaching applications across engineering, mathematics, physics, and other sciences. And the concept of approximating a function or data using a series of functions is a fundamental tool in modern science and engineering. Here I am going to illustrate how we can expand an analytic function at a point using Taylor series. Just for an illustration, we know sin z is an entire function. That means it is analytic everywhere in the entire complex plane. So you can expand sin z in the form of an infinite series containing positive powers of z minus a, where a can be any point in the complex plane. If you suppose a equal to pi, you can expand sin z in the form of an infinite series containing positive powers of z minus pi. If a is minus pi, then we can express sin z in the form of an infinite series containing positive powers of z plus pi. If a is 0, then we can expand sin z in the form of an infinite series containing positive powers of z. If a is 2 pi, then corresponding series will be an infinite series of positive powers of z minus 2 pi. If a is 3 pi by 2, then sin z can be expressed in the form of an infinite series containing positive powers of z minus 3 pi by 2. See, in this way you can expand by using Taylor series. So consider a question. Find Taylor series of cosz z at z equal to pi by 2. Really, this question is, you have to express cosz z in the form of an infinite series containing positive powers of z minus pi by 2. Here a is pi by 2. So for getting this expansion, we have to use Taylor series. So we have to find f of pi by 2, f dash pi by 2, f2 dash pi by 2, etc. Here given fz equal to cosz z and a equal to pi by 2. For that, you take the successive derivative of fz, that is f dash z, f2 dash z, etc. Here fz is cosz z, f dash z is minus sin z, f2 dash z is minus cos z. Next you find f of pi by 2. It is 0, f dash pi by 2 minus 1, f2 dash pi by 2 is 0. Now we got only one non-zero term, which is f dash pi by 2 minus 1. Whenever we give the expansion of a function in the form of an infinite series, we must mention at least 3 non-zero terms in the series. So here we have to find at least 3 non-zero values in which successive derivative of f at pi by 2. So next you write f3 dash, f4 dash, etc. until we will get 3 non-zero values. Here f3 dash z is sin z, f4 dash z is cos z, f5 dash z is minus sin z. Next f3 of pi by 2, 1, f4 at pi by 2 is 0, f5 at pi by 2 is minus 1. Now we have 3 non-zero values, minus 1, 1, minus 1. Next consider the Taylor series, and here you have to replace a by pi by 2. Next you replace f of pi by 2, f dash pi by 2, f2 dash pi by 2 extra by its values. Here f pi by 2 is 0, so first term is 0. In second term, f dash pi by 2 is minus 1, so minus of z minus pi by 2 by 1 factorial. Here f2 dash pi by 2 is 0, so that term will be absent. f3 dash pi by 2 is 1, so corresponding term will be z minus pi by 2 the whole cube by 3 factorial. And next term is 0, since f4 at pi by 2 is 0. And the next term is minus z minus pi by 2 the whole raised to 5 by 5 factorial. Now we have three non-zero terms, so you can give the expansion of fz as fz equal to minus of, here fz is cos z, fz is minus z minus pi by 2 by 1 factorial plus z minus pi by 2 the whole cube by 3 factorial minus z minus pi by 2 the whole raised to 5 by 5 factorial plus etc. See, remember it is an infinite series. See, this is the expansion of cos z at pi by 2. See, clearly it is an infinite series containing positive powers of z minus pi by 2. Next, consider another question. Find Taylor series of sin z at z equal to pi by 4. Here fz is sin z and a is pi by 4. Really, we have to express sin z in the form of an infinite series containing positive powers of z minus pi by 4. So you find the successive derivative of f and evaluate these at pi by 4. We have fz is sin z, f dash z is cos z, f2 dash z is minus sin z. Next, f of pi by 4 is 1 by root 2, f dash pi by 4 is 1 by root 2, f2 dash pi by 4 is minus 1 by root 2. Now we have three non-zero values, so we can stop this procedure. Next, consider Taylor series. You put z equal to a and write the values of f at pi by 4, f dash pi by 4, f2 dash pi by 4. So we have sin z is 1 by root 2 plus 1 by root 2 into z minus pi by 4 by 1 factorial minus 1 by root 2 into z minus pi by 4 the whole square by 2 factorial plus etc. Clearly, sin z is in the form of an infinite series containing positive powers of z minus pi by 4. Next, consider one more question. Question is, express z by z plus 1 into z plus 2 in the form of an infinite series containing positive powers of z minus 1. Here you have to apply Taylor series. Since fz is a quotient, it is better to write its partial fraction for the smooth calculation of its successive derivatives. Otherwise, it is too difficult for finding its successive derivatives since it is a quotient. So first, fz in the form of its partial fraction, that is a by z plus 1 plus b by z plus 2. You find a and b, you can see a is minus 1 and b is 2. So fz is minus 1 by z plus 1 plus 2 by z plus 2. So rewrite 1 by z plus 1 as z plus 1 raised to minus 1. So you can see fz is minus of z plus 1 raised to minus 1 plus 2 into z plus 2 raised to minus 1. Next, take its first derivative. F dash z equal to, we know derivative of x raised to n is nx raised to n minus 1. You apply this result for each term. So derivative of the first term is minus into minus 1 into z plus 1 raised to minus 2. Minus into minus becomes plus. So the f dash z is z plus 1 the whole raised to minus 2. Next, derivative of next term is minus 1 into z plus 2 raised to minus 2. That becomes minus 2 into z plus 2 raised to minus 2. Next, f2 dash z. Derivative of first term is minus 2 into z plus 1 raised to minus 3. Derivative of second term is minus 2 into z plus 2 raised to minus 3. Minus 2 into minus 2 becomes plus 4. So f2 dash z is minus 2 into z plus 1 raised to minus 3 plus 4 into z plus 2 raised to minus 3. Next, find f1, f dash 1, f2 dash 1. You can see f of 1 is 1 by 6, f dash 1 is 1 by 36, f2 dash 1 is minus 11 by 106. We have three non-zero terms. Next, you write the Taylor series, and in this you put a equal to 1 and substitute the values of f of 1, f dash 1, f2 dash 1. And we can see the series is z by z plus 1 into z plus 2 is 1 by 6 plus 1 by 36 into z minus 1 by 1 factorial minus 11 by 108 into z minus 1 the whole square by 2 factorial plus etc. Next series is Maclaurin series. See, it's a special type of Taylor series when a equal to 0. See, we have the Taylor series. See, in this, if we keep a as 0, we get the series as f of z equal to f of 0 plus z into f dash 0 plus z square by 2 factorial f2 dash 0 plus etc. And this series is known as Maclaurin series. And it is named after a Scottish mathematician called Maclaurin, who made important contributions to geometry and algebra. Advantage of this series is we can give series expansion of any function which is analytic at 0 by using Maclaurin series. We are familiar with these series. Have you ever think why e raised to z equal to 1 plus z by 1 factorial plus z square by 2 factorial plus z cube by 3 factorial plus etc. Similarly, sin z, cos z, etc. Really, these expansions are based on Maclaurin series. Just for an illustration, let me find the series expansion of e raised to z by using Maclaurin series. Let f z equal to e raised to z. F dash z is e raised to z, f2 dash z is e raised to z. We know successive derivative of e raised to z is e raised to z itself. Next to find these at 0. So f0 is e raised to 0, e raised to 0 is 1. So f0 is 1. Similarly, f dash 0 1, f2 dash 0 1. Next, you consider Maclaurin series and you put a equal to 0 and substitute the values of f0, f dash 0, f2 dash 0, etc. Then you can see e raised to z is equal to 1 plus z by 1 factorial plus z square by 2 factorial plus etc. Next question, find the series expansion of 1 by 1 plus z. See, already we studied two types of series, Taylor series and Maclaurin series. See, in this question, the point A is not given. You keep in your mind, if the point is not given, you have to take A as 0. So here, you have to take A equal to 0. When A equal to 0, the corresponding series will be Maclaurin series. See, Maclaurin series is a special type of Taylor series when A equal to 0. So here, really the question is, find the Maclaurin series of 1 by 1 plus z. Let fz equal to 1 by 1 plus z. Next, for the convenience of taking its successive derivative, you rewrite 1 by 1 plus z as 1 plus z raised to minus 1. So fz is 1 plus z raised to minus 1. F dash z is, here the term is in the form x raised to n, its derivative is nx raised to n. So its derivative is minus 1 into 1 plus z raised to minus 1 minus 1, that is minus 2. So f dash z is minus of 1 plus z raised to minus 2. Next, f2 dash z is minus 1 into minus 2 into 1 plus z raised to minus 3, that is 2 into 1 plus z raised to minus 3. Here minus 1 into minus 2 becomes 2. f3 dash is 2 into minus 3 into 1 plus z raised to minus 4, that is minus 6 into 1 plus z raised to minus 4. Next to find these at 0. So f0 1, f dash 0 minus 1, f2 dash 0 2, f3 dash 0 minus 6. Next you consider Maclaurin series and you put a equal to 0 and replace the values of f0, f dash 0, f2 dash 0, f3 dash 0 by 1 minus 1, 2 minus 6. So you can see 1 by 1 plus z is equal to 1 minus z by 1 factorial plus 2 into z square by 2 factorial minus 6 into z cube by 3 factorial plus etc. See, this is an important series which has lot of applications in many situations, and especially we use the series in the next type of series, which is Lorentz series. So we rearrange the terms in the series in a beautiful manner. Here you see this third term, it is 2z square by 2 factorial, that is z square. Next fourth term, it is 6z cube by 3 factorial, 6 by 3 factorial, that is 1. So we can rewrite the term as minus z cube. Similarly, the next term will be plus z raised to 4, etc. So we have 1 by 1 plus z equal to 1 minus z plus z square minus z cube plus etc. Next question is expand log 1 plus z. Here a is not mentioned, you take a as 0, and really the question is you find the Maclaurin series of log 1 plus z. Let f z equal to log 1 plus z. F dash z is 1 by 1 plus z. Next you rewrite 1 by 1 plus z as 1 plus z raised to minus 1 for the convenience of taking its successive derivatives. So you consider f dash z is 1 plus z raised to minus 1. F2 dash z is minus 1 into 1 plus z raised to minus 2 as we did in the previous question. F3 dash z is 2 into 1 plus z raised to minus 3. Next we find these at 0. F0 is log 1, which is 0. F dash 0, 1. F2 dash 0, minus 1. F3 dash 0, 2. Next you consider the Maclaurin series and put a equal to 0 and substitute the values of f dash 0, f2 dash 0, f3 dash 0, etc. You can see log 1 plus z is z by 1 factorial minus z square by 2 factorial plus 2z cube by 3 factorial minus etc. See, log 1 plus z is a standard function, so we must know its expansion. So for getting a beautiful series, we have to rearrange the terms. So the first term is z, second term is minus z square by 2 factorial. In the third term, there is a simplification. After the cancellation, you can see third term is z cube by 3. If you find the fourth derivative of fz and f for 0, you can see f4 at 0 is minus 6. And if you put this in the Maclaurin series, you can see the next term is minus z raised to 4 by 4. After the cancellation of 6 by 4 factorial, there is no factorial in the denominator. So similarly, if you find the fifth derivative etc. and after simplification, you can see in the series the denominator is free from factorial. So you consider the second term of the series as minus z square by 2 instead of writing 2 factorial. So finally we can observe log 1 plus z is z minus z square by 2 plus z cube by 3 minus z raised to 4 by 4 plus etc. In a similar way, we can also give the expansion of hyperbolic functions in the form of an infinite series. Among the 6 hyperbolic functions, sin hz and cos hz has some importance. Let me expand sin hz in the form of an infinite series. So let fz equal to sin hz. We know derivative of sin hz is cos hz and derivative of cos hz is sin hz. So f dash z is cos hz, f2 dash z is sin hz, f3 dash z is cos hz. Next, you keep in your mind sin h0 is 0 and cos h0 is 1. Because we have sin hx is e raised to x minus e raised to minus x by 2. In this you put x equal to 0, then you can see sin h0 is 0. Also we have cos hx is e raised to x plus e raised to minus x by 2. Here you put x equal to 0, then you can see cos h0 is 1. So we have f0 is 0, f dash 0 is 1, f2 dash 0 is 0, f3 dash 0 is 1. While expressing a function in the form of an infinite series, we have to mention at least 3 non-zero terms in the series. So next evaluate f4 dash z, which is sin hz, f5 dash z is cos hz. You can see fourth derivative of f at 0 is 0 and fifth derivative of f at 0 is 1. Now we have 3 non-zero values, which is f dash 0 1, f3 dash 0 1, f5 dash 0 1. Next consider Maclaurin series. In this you put a equal to 0 and substitute the values of f0, f dash 0, f2 dash 0 etc. Then we can see Sin hz is z plus z cube by 3 factorial plus z raised to 5 by 5 factorial plus etc. By using Maclaurin series, we can see cos hz is 1 plus z square by 2 factorial plus z raised to 4 by 4 factorial plus etc. Let's enjoy the beauty of the series sin z, sin hz, cos z, cos hz. Thank you for watching.